Black holes represent one of the most fascinating and enigmatic phenomena in the universe, challenging our understanding of physics, space, and time. Predicted by Albert Einstein's general theory of relativity in 1915, these cosmic entities are regions where gravity is so intense that nothing, not even light, can escape once it crosses a boundary known as the event horizon. But how do black holes form? What are their key properties, and how do we detect them? This part delves into the scientific foundations, drawing on established astrophysics to provide a clear picture. The formation of a black hole typically begins with the death of a massive star. Stars shine through nuclear fusion, converting hydrogen into helium and heavier elements in their cores. For stars with masses at least 8 times that of our Sun, about 1.989 times 10 to the 30th kilograms, this process eventually exhausts the fuel, leading to a catastrophic collapse. When the core can no longer support itself against gravity, after fusing elements up to iron, which yields no net energy, the outer layers explode in a supernova, one of the brightest events in the cosmos. What's left is a dense remnant. If this core's mass exceeds about 3 solar masses, the Tolman-Oppenheimer-Volkoff limit, gravity overwhelms neutron degeneracy pressure, and the core collapses into a singularity, a point of infinite density where the laws of physics as we know them break down. Not all black holes form this way. Stellar black holes, the most common type, range from about 3 to 20 solar masses and span roughly 10 to 100 kilometers in diameter. Supermassive black holes, however, lurk at the centers of galaxies, including our Milky Way's Sagittarius A, which boasts a mass of around 4 million suns and a diameter comparable to the orbit of Mercury. These giants likely form through mergers of smaller black holes or the direct collapse of massive gas clouds in the early universe. There's also evidence for intermediate mass black holes, hundreds to thousands of solar masses in globular clusters. Though they're rarer, a black hole's defining property is its event horizon, calculated by the Schwarzschild radius, Rs equals 2gm/c squared, where g is the gravitational constant, m is mass, and c is the speed of light. For a solar mass black hole, this radius is about 3 kilometers. For Sagittarius A, it's around 12 million kilometers. Beyond mass, black holes are characterized by charge and spin, angular momentum, as per the no-hair theorem, which states they have no other distinguishing features. Hence, they're remarkably simple, despite their complexity. Gravity near a black hole is extreme due to space-time curvature. Imagine space-time as a rubber sheet. A star dents it, but a black hole punches a bottomless well. This curvature warps light paths, creating effects like gravitational lensing, where distant objects appear distorted. Tidal forces, arising from gravity's variation over distance, can tear apart approaching objects in a process called spaghettification. For smaller black holes, these forces are lethal, far from the horizon. For supermassive ones, they're milder, allowing hypothetical crossings without immediate destruction. Detection of black holes isn't direct, as they're invisible. Instead, we infer their presence from effects on surroundings. In binary systems, a black hole can accrete matter from a companion star, heating it to millions of degrees and emitting X-rays detectable by telescopes like Chandra. Gravitational waves, ripples in space-time from merging black holes, were first observed by LIGO in 2015, confirming Einstein's predictions and opening a new era of astronomy. The Event Horizon Telescope captured the first image of a black hole in 2019, the shadow of M87's event horizon against its glowing accretion disk, followed by Sagittarius A in 2022. Theoretical radiation adds intrigue. Stephen Hawking proposed in 1974 that quantum effects near the event horizon create particle-antiparticle pairs, with one escaping as Hawking radiation, causing slow evaporation over eons. For stellar black holes, this process takes 10 to the 67th years, far longer than the universe's age, making it unobservable. Primordial black holes from the Big Bang might evaporate faster, potentially explaining some gamma-ray bursts, though this remains speculative. In summary, black holes are not voids, but compressed matter reshaping reality. Their study blends observation and theory, revealing the universe's extremes. From stellar remnants to galactic anchors, they embody gravity's triumph, setting the stage for what happens if one were to venture too close. Imagine yourself as an intrepid astronaut drifting through the cosmos in search of new worlds, only to encounter the inescapable pull of a black hole. What would happen if you fell into one? This scenario, while purely hypothetical for humans, given current technology, allows us to explore the mind-bending physics of general relativity and quantum mechanics. In this part, we'll simulate the journey step by step, from initial approach to crossing the event horizon, focusing on the physical forces at play and the surreal human experience. We'll emphasize supermassive black holes like Sagittarius A at our galaxy's center, where survival might last longer than with smaller stellar ones. As you approach a black hole, the first noticeable effect is gravitational acceleration. Black holes don't suck like vacuums. They warp space-time, causing objects to follow curved paths toward them. From afar, say millions of kilometers out, the gravity feels similar to orbiting a star of equivalent mass. Your spacecraft might detect increased orbital speeds or distorted starlight due to gravitational lensing, where the black hole bends light rays, creating eerie rings or multiple images of background galaxies. Visually, you'd see a growing sphere of darkness encircled by a photon ring, where light orbits unstably before either escaping or plunging in. Drawing closer, tidal forces become critical. These arise because gravity weakens with distance, so parts of your body or ship nearer the black hole experience stronger pull than farther parts. For a stellar black hole, 10 to 20 solar masses, event horizon about 30 to 60 kilometers across, spaghettification, stretching into a thin strand, occurs well outside the horizon. If falling feet first, your feet accelerate faster than your head, generating forces equivalent to thousands of Gs. Calculations show that for a 10 solar mass black hole, at about 150 kilometers out, the tidal acceleration difference across a 2-meter human is around 10 to the 6th meters per second squared, ripping atoms apart before you reach the horizon. It's a gruesome end. Molecular bonds break, turning you into plasma. Opt for a supermassive black hole to survive longer. Sagittarius A, with 4 million solar masses and an event horizon about 24 million kilometers wide, about 17 times the Sun's diameter, has gentler tides. The tidal force scales inversely with the cube of the radius, so larger horizons mean weaker gradients. Here, you could cross the event horizon intact. As you near it, time dilation kicks in. From your perspective, the fall feels normal. General relativity ensures you experience proper time without noticing the horizon's crossing. But to a distant observer, your motion slows asymptotically. You appear to freeze at the horizon, redshifted into invisibility as light waves stretch to infinite wavelengths. What do you feel during the descent? Acceleration builds, but freefall means no sensation of weight. You're in orbit, albeit a fatal one. However, any deviation, like thrusters firing, would reveal immense gravity. Nearing the horizon, the sky warps. Stars compress into a bright band overhead, while below stretches darkness. This is frame dragging. If the black hole spins, most do per Kerr metric, twisting spacetime like a vortex and potentially enabling energy extraction via the Penrose process. Crossing the event horizon is a point of no return. Inside, radial direction becomes time-like. Space flows inward, faster than light, like a river over a waterfall. You can't turn back, any more than you can reverse time. The journey to the singularity takes finite proper time. For Sagittarius A, about 10 minutes from horizon to center. Per rough estimates, using the Schwarzschild metric for free fall from rest at horizon. But actual paths vary. As you plummet, tides intensify near the singularity. Density skyrockets. Curvature becomes infinite, and quantum gravity effects, unresolved in current theories, might dominate. Human experience adds a psychological layer. Isolation is profound. No signals escape, so you're cut off from the universe. Hallucinations from stress or radiation? Hawking radiation, though negligible for large black holes, might produce subtle particle fluxes. More pressing, accretion disk radiation if the black hole is active, bombarding you with X-rays and gamma rays, potentially fatal before the horizon. In extremis, what philosophical insights? The fall underscores relativity's counterintuitive nature. Your time is finite, yet to outsiders, you're eternally poised. It highlights human fragility against cosmic scales. Our bodies, evolved for Earth's 1G, can't withstand such extremes. Yet, it inspires. Black holes probe physics's frontiers, from event horizons testing relativity to singularities demanding quantum gravity unification. This hypothetical plunge reveals black holes as dynamic traps, not static voids. While doom awaits, the physics enriches our cosmic understanding, bridging theory and imagination. Black holes continue to spark intense debates in theoretical physics, pushing the boundaries of our understanding of the universe. At the heart of these controversies lies the information paradox, first highlighted by Stephen Hawking in the 1970s. When matter falls into a black hole, it seemingly vanishes, taking its information, details about its quantum state, with it. Hawking's calculations suggested that as black holes evaporate through radiation, this information is lost forever, violating quantum mechanics' principle that information must be conserved. This clash between general relativity and quantum theory has fueled decades of research, with proposed resolutions like the holographic principle, which posits that all information inside a black hole is encoded on its event horizon, like a 2D hologram projecting a 3D reality. Another contentious area is the nature of the singularity. General relativity predicts a point of infinite density at a black hole's core, where space-time curvature becomes boundless and physics breaks down. Critics argue this signals the theory's incompleteness, as infinities often indicate missing pieces, much like how quantum mechanics resolved atomic infinities. Quantum gravity theories, such as loop quantum gravity or string theory, suggest singularities might be avoided. In loop quantum gravity, space-time is quantized into discrete loops, potentially replacing the singularity with a bounce, where collapsing matter rebounds, forming a white hole that expels everything. String theory envisions black holes as fuzzy balls of strings, smoothing out infinities. These ideas remain untested, but they imply black holes could be portals or recyclers of matter, challenging the classical no-escape view. Firewall hypothesis adds fuel to the fire. Proposed by physicists like Joseph Polchinski, it suggests that to preserve information, the event horizon might be replaced by a searing wall of high-energy particles, a firewall, that incinerates anything crossing it. This contradicts relativity's equivalence principle, which states that free-falling observers shouldn't notice anything special at the horizon. The debate rages: is the horizon smooth or deadly? Recent advancements, including ADS-CFT correspondence, a duality between gravity in anti-de Sitter space and conformal field theory, hint at resolutions where entanglement preserves information without firewalls. But consensus is elusive. Beyond theory, black holes have profound implications for cosmology and our place in the universe. They regulate galaxy evolution. Supermassive black holes influence star formation by heating gas through jets and outflows, as seen in quasars. Without them, galaxies might collapse or fail to form spirals like the Milky Way. On a grander scale, black hole mergers detected by LIGO and Virgo reveal a hidden population, suggesting the early universe was seedier with primordial black holes, possibly explaining dark matter. If true, these relics from the Big Bang could account for the invisible mass holding galaxies together, reshaping our models of cosmic structure. Philosophically, black holes probe reality's fabric, Time dilation near horizons questions causality and free will. What does it mean if your fate is frozen for external observers? They also inspire multiverse speculations. Some models propose that singularities birth new universes, with our own potentially emerging from a prior black hole. This black hole cosmology aligns with eternal inflation theories, where universes bubble off endlessly. Looking ahead, future explorations promise breakthroughs. Next-generation telescopes like the James Webb Space Telescope and the Extremely Large Telescope will peer deeper, capturing black hole births in the universe's infancy. Gravitational wave observatories, including space-based LISA, set for 2030's launch, will detect supermassive mergers, mapping cosmic history. Quantum computing might simulate black hole interiors, testing theories inaccessible to experiments. Meanwhile, the Event Horizon Telescope aims for sharper images, potentially revealing spin and charge details. Human implications extend to technology and ethics. Understanding black holes could advance energy extraction methods, like harnessing rotating ones via the Blandford-Znajek process for limitless power. But ethical dilemmas arise. Should we risk probing them with probes, knowing information might be lost? Popular culture amplifies this. Films like Interstellar dramatize traversable wormholes, stabilized black holes, sparking public interest but often blurring fact and fiction. Ultimately, black holes embody the unknown, driving innovation. As we unravel their mysteries, we edge closer to a unified theory of everything, blending gravity with the quantum realm. Whether as destroyers or creators, they remind us of the universe's vast, humbling complexity, urging continued curiosity and exploration.